Hey, you guys. Live from the hospital. Well, not live for you, but I'm at the hospital and hanging with Graham here. He's in my lap right now. Finished a bottle off. He's doing tons better. If at the end I have a chance, I'll throw a picture up of the two of us just moments ago. You hear that cough. That actually is better. And he's doing pretty well. He's trying to play with things that are not the iPad, so pardon me if there's some weird interruption in this. So here goes. That first problem, it says, show the rate at which the water is pumped from a storage tank. Now, I went ahead and put all the work up there for you, but the big deal is net change we've done before, but we need some of these techniques. There's some nuances to them we've got to review, and they help us with other stuff later. One thing we have to remember is we've got a rate of change, like gallons per hour. If you integrate it, what you get is gallons, of net gallons accumulated on a given interval. And if you want to approximate it, you can approximate area with whatever shape you want. I'm going to do a trapezoid here. And so this is 24, it's got a height of 24. 1/2 24, and then the 250 to 250. I just went ahead and kind of put a straight line from lower corner to upper corner there and called it a trapezoid. So that was my take on this one. About $3,600. And we're moving on to number 2. That's a nice warm up. 2 is, no more difficult, but there's something about this one too. It says it's an acceleration graph, and we're supposed to answer questions related to velocity. So net change, generally, it has to do with, you're going to take an integral of some rate, and what it's going to do is knock you back a degree. So if I do acceleration as the data I have, if I integrate, I'm going to get something that speaks toward velocity, a degree back. So, and the other thing we want to talk about is units. This is a really good time. He just threw his remote on the floor. We'll find it. We'll go get it. And then, you want something else to play with? Okay, hang in there. We'll show something. The class is listening to us, okay. So here it is. There's some area that we're calculating. Acceleration and time are the units in this graph. And I just threw in a rough graph. Nothing major. Yeah, uh-oh. Yeah, oh, man. I know, uh-oh. It fell on the floor, huh. And there's feet. So let's look at this area. Acceleration is feet per second squared. Time is in seconds. So if you do an area of that little shaded region I have, it's going to be in our length by width units, feet per second squared by seconds, and that's multiplication in there. What we get out is feet per second, which is a measure of velocity. So if you remember, if you actually calculate the area and do unit analysis, it'll give you the appropriate unit for that net change that you want to accumulate. That becomes really important in a later problem. Hang on, Graham is shifting dramatically. I'm going to pause. Okay, that was a little pause. You maybe didn't notice, but. All right, Graham, you comfy? Good boy. All right, so what we have is we're going to get feet per second, which is great. Notice all the answer choices are in feet per second. So let's be more precise. It says go in there and approximate using trapezoidal sums. Well, that's only part of it. We can do trapezoids, no problem. So just imagine, yes, we are going to do trapezoids of the graph up above, but if you just did trapezoids of that and gave an answer, that answer choice is available to us, but it would be the wrong answer because you're missing one key element, which is that if you're going to get the velocity at 15 seconds in this particular graph, and what you're going to have to account for is that this net change, this integral that you take, is how much change in velocity occurred from time 0 to 15. And if you want to find out what your actual velocity is at a particular point, you have to take into account your original velocity, then add to it whatever the change was, and I say net because it could be a loss or a gain, and that'll give you your final velocity at that moment. So we start at 5 miles per hour. This says your initial velocity. Ow, you guys, is that okay? 5 miles per hour. What we're going to add to it is the net change, that 0 to 15 approximation that we're going to use with that acceleration graph. Yeah, did you find that? So here we go. This, I got to go find the trapezoidal approximation of that integral part. We got the 5, that's our initial amount. Let's find out that trapezoidal. Let's do a little, okay, 3 is definitely the continuous height of those trapezoids. So 1/2 3. And do you remember with trapezoids you do the first height once, all the internal heights twice, and the last height once. And that's what I have before you. Hey, and anytime you guys want to ask for a pause and think about this or send someone to the board to explain some more, do it. It's your prerogative. So there it is. There's our trapezoidal sum. It gives you 120. So what we get is, hey, look, answer C's got 120 in it. And you'd be wrong, so be careful. But we want to get the velocity at 15 seconds, which is not just 120, but it's starting with 5 and changing 120 miles per hour, we end up with, and that's an increase, by the way, positive, we get it 125 feet per second. I keep saying miles per hour, don't I? Oh well. So, feet per second. Let's roll with that a little bit slower. Okay, a rate at which customers arrive at a there we are. I can't read that. I got a little thing in front of mine. They arrive at this counter to be served. Wouldn't this be awesome to be such a business owner that you model your arrival of customers with an actual function? Wouldn't that be awesome? Imagine that. I bet there's somebody out in this world that's done this. So, quick attack on this one. There are great problems out there where all you have to do, if you have a calculator in front of you, is integrate the function on the given interval. If you have a rate of change function and you want to find total change, so this is people arriving at the counter, you're going to get total people if you integrate it. I'd put it in Y1 and rock and roll. Oh, hang on there, Graham. Okay, you get 724.645. You round to the nearest whole, and there you go. So nothing fancy there. Right, buddy? Then the next option, we're going to pause again. Okay, so there's that one, no problemo. But the next one, alright, so we got pollution being removed from a lake, number 4. There's a rate of change function again. If you want total change, you just integrate on that particular interval, right? Speedy, quick, easy, have a calculator handy, and let the calculator do the work. And that is just fine. And I actually, does that not look, that's the weirdest 40 I've ever written. It looks like 4 pi. Anyway, keep on going. 5, we've got this developing country consumes oil at a particular rate, so many millions of barrels per year. So on this particular interval, how would we find, the amount of oil? Well, you guys have got this down, right? The integral of the rate of change. Just be careful. You're given a rate of change, so you're going to integrate that function. Don't throw any primes or other crazy wonkiness in there. But, yeah, D. You just want to do the integral of the rate of change. That's what you've been given. And that'll give you net change for that respective variable. Okay. Those are the quick and easy. The biggest thing I think to remember is that initial value, that initial velocity function. That's the tricky one that we had just a minute ago. 6. All right, so there's this temperature thing. This is a really fun problem. And this is one of those, remember when we came up with nonsense units with, those of you who had Dr. Sherman around, and then 4th block, we still talked about this. We had these nonsense units. We integrated something and we got foot-pounds or weird stuff. Well, actually foot-pounds is torque. But we had other stuff that was, nonsensical. Well, it turns out this nonsensical integral that we get in this problem here is actually going to pay off and be useful. But first let's talk about the A part. It says find the average temperature. So if you got average involved and you have a temperature outside modeled by a function, the average value of any given function is to integrate that function on the interval and then divide it by the interval itself, the length of the interval. So just keep that. That's one of the best. Average comes up on a question on the AP exam. It's 9 times out of 10. It's going to be an average value function like this. Pull out the calculator, rock and roll. Okay, but B, let's get a graph going. That's a really rough graph, and there's that average value we just calculated thrown into the graph, just to give you some perspective. So here you are, is a little graph of our situation. It says an air conditioner cooled the house whenever the temperature was at or above 78. Probably should throw 78 in there too. Let's do that. And it says what values of T was the air conditioner cooling the house. So basically we want to find out where that T1 and T2 are. And then it would just be the interval of the values between that. So here's T1. I'm going to stow it, by the way, in A and then B, because if you notice in part C, it asks you to use it again. So this stowage that we have in our calculator is going to be very handy. Okay, so 5.23, 18.769. You guys know how to do that, right? Graph that. You go second trace, do the calculate for the intersections, and voila. Stow it. Oh, Grant, good job, buddy. So now, part C, we're going to utilize this information. And, alright, so let's get this graph back out there. We got degrees, Fahrenheit, we got hours, we got this 78 degrees, and then we got this area above it. It's going to cool the house anytime the temperature is above that particular temperature. That's the context of that part C. So that area, I wanted to kind of tell you again, if we were going to have to integrate that, just because that's the section we're in, we would get degrees by hours. The width and height of that would be, so many degrees by so many hours. Degree hours are not their nonsensical unit. Seems ridiculous, right? Well, hang in there. What I want to know for this particular problem is how much money are we going to charge if it's 5 cents per degree every hour after, you go over a certain temperature. If you want to go back to part C and read it again, or you're reading it now, that's the idea. But we want to know money. I want money. You guys, boy, that joke the other day. I want the integral of e to the x. That's, oh my word. Anyway, so there it is. I want money. So money, $0.05. This is the unit that you're given. Okay, this 5 cents per hour every degree greater than 78. Am I greater than sign in there? Yes, looks like another 7, but that is degree greater than 78, not 778. And if you go 5 cents per hour per degree greater than 78, that's like a double division, right? When you divide a denominator by another number, it's just the product of those two. So we've got dollars per hour time degree. Again, ridiculous. Well, think of, if my goal in the end is to get just dollars, if I took that 0.05 and multiplied it by something with a unit that would cancel that hour degree out, I'd have dollars left. If only I could multiply by something with a unit's degrees times hours or hours times degrees, that would be amazing. Oh wait, I've got that. So it turns out the area of that between that 78 degree line and the curve up above, the hour degree, cancels with the denominator of that unit on our 5 cents per hour per degree above something, and we get the dollars charged. This actually is what happens if you go read a statement, like your therms used when you do your calculations for whenever you're doing your temperature for your house. There's this hour degree unit they throw out there, or degree hour. And you're going, what on earth is that? Well, this is the degree hour thing they're talking about. So anyway, we could investigate that further on another day. It actually is used, and maybe it's not as nonsensical as we thought. Cool. So we actually take that integral because it produces the correct unit to cancel with my given unit, so that I can find out dollars, a measurable unit of dollars, of interest in the end. Okay? Remember, the integral is what produced that degree times hours unit. Well, let's get to work. We've got to get that integral. So we're going to take 0.05 times that integral with the crazy unit, and we're only going to do it from 5.23 to 18.7629 because that's the region of time. It says any time when we're above 78 degrees, we're going to cool the place. So just do the function. Now, you stowed that in A and B, right? So your integral, you can just put A and B, and then you can do y1 has your function in it. Just take it all times 0.05. I mean, this could be really efficient if you stow an A and B. It'd be pretty cool. And you round either 5.09 or 5.10. The cool thing about free response questions is there's nothing specified. You can round up or down, and both are correct. They won't count you wrong. Then on the number 7, and I'll see how far I get. Graham's falling asleep on me, so we'll just go until he's asleep, and then I'll just make a part 2 to this video series. And maybe I'll talk louder, slower, or neither. I don't know. We'll see how it goes. Let's check this out. Part A, 7A, says, hey, look at this. This is people entering and people leaving the museum, or amusement park. And there's functions for that kind of stuff. Imagine if you actually got functions for that kind of stuff. You could be like the savior of your company. You should think about doing that. Model behavior, human behavior. You'll be a phenom at your company. So, how many people have entered the park? 5 p.m. Let's see, until 5 p.m. Round your answer to the nearest whole number. So, remember, the park's open only from 9 to 23. Time equals 9. There's nobody in the park when they open, and 23 is like 11 o'clock at night. 23, they're using the 24-hour clock. But we're interested in how many people enter the park from opening until 5 p.m. So that's 9 to 17. Use the entering function, integrate, use your calculator, 6,004 people. Now, the price of admission to the park, 15 buckaroos. Whoa, what just happened there? I guess that's where I ended on my notes. Alright, we're going to say part 2 is going to kick in. Why don't you guys start working on this? You can totally get part B without much thought. I think you can do C and D as well. Keep rocking. I'll make video 2 here real soon. You can press play whenever you like. Go back and do this. So, Graham, I'm going to say bye for now, since you're going to fall asleep on me. Okay, see you guys.